Hello, welcome back to Function Operations. In part 3, we're looking at products and quotients. So we've looked at sums and differences graphically. We've taken a quick glance at sums and differences algebraically. And now algebraic products and quotients. We'll see some similarities. There's a fair amount of straightforwardness to the proceedings here. So with products, for example, when we're asked to multiply things together by one of these notations, we do just that. We do just multiply them together. In this example, we're going to take f times g of x. We say it's f of x times g of x, where f of x is x plus 4, and g of x is 2x minus 3. If we were supposed to be graphing from this at this point, I would probably leave it in factored form, just because as we've seen from polynomial functions, factored form gives us some valuable information, for example, the zeros. But if we're just stating the equation of it, we could probably kind of leave it there. But simplified, we're talking about just expanding this, collecting like terms. All that FOIL business. Do you know what you feel? So there's h of x. It's the product of f and g. It's the product of x plus 4 and 2x minus 3. That's where it comes from. When we look at the domain, just as we did with sums and differences, the domain of the product function is only what's common between the domains of the original functions. Now in this case, the domain of f, well, it's a linear function, so we're talking about all reals. And the domain of g, also a linear function, also all reals. So if f and g both exist everywhere, then their product must also exist everywhere. And we can say the domain of h, their product function, is also all real numbers. And everyone lived happily ever after. Ever after? Nah, can't take it back now. We on video. The end. Quick, try the next one for funsies. Because you can. Don't forget all that business about the fact that you can pause this video if you want. Run it at your own time. Replay the example if need be. But ahead I go. H of x is the product of f and g. F of x is x squared minus 5. G of x is x squared plus 2x plus 2. There's your product function. If you choose to expand and simplify, you'll get some stuff. Sorry about the fact that you're hearing this pen hit the surface of this device every single time I write something. In the quietude of this environment, it honestly kind of bothers me. Oh, that's life. Missing all your voices. Here in this case, domain of a quadratic function, being a polynomial function, is all reals. So f exists over all real numbers, g exists over all real numbers, therefore h, its product, also exists over all real numbers. And finally, this last example. Once again, taking the product. So f of x is the square root of x. G of x is the square root of x plus 2. We're multiplying those. And if we have two radicals with the same index being multiplied, we can just apply that that index, that root, to the product of those radicands. So x times x plus 2. And if we simplify that, ta-da. This, on its own, has its own set domain. There are areas where we can take the square root of it, areas where we can't, all depending on what the value of x is. It is slightly more restricted just because of the domains of its factor functions. So when we look at the domain of f, square root of x is what we're dealing with, therefore x must be at least 0. Whoa! Are you serial? Oh, shapes. And for g, x has to be at least negative 2. But for h of x, the product function, what do we do there? We take whatever's common. Now obviously, nothing less than negative 2 is going to be common to both because it's not in either of them. But even a value like negative 1 will not work. Negative 1 is all fine and dandy over here. It meets that criteria. It doesn't meet this criteria. So that overlapping region is only where x is greater than or equal to 0. And again, you could put that in interval notation if you want. World's your oyster. But there's the answer to this one. Questions, comments, concerns? I know I jokingly say that in all the videos, but again, reminder, don't forget to actually ask me if you have questions. And/or comments. And/or concerns. Sorry, I had to take a big stretch. Oh. We have 3 more examples. These first 3 examples were all about products, but as stated in this title, we're looking at quotients too. There's a lot that's common. Procedurally, we're just performing the operation. But we could have an additional restriction in our quotient functions domain, because we know that we can't divide by 0. So if g of x is equal to 0, that's bad. We do not want g of x to equal 0. It will cause restrictions in our domain. Again, because we cannot divide by 0. So when we find the common domain for the domain for h of x, the quotient function, we'll look at what overlaps. We'll look at what's common to both f and g. That's still necessary. But we'll also take into account where g of x is equal to 0 and say that x cannot be those. Do you feel? Yeah, definitely feel. Woo! Here is one. Ooh, blue. Equation-wise, we're just going to replace that with f of x. We're going to replace this with g of x. and go from there. So h of x is just straight up f of x divided by g of x. Beautiful. But its domain. We look at the domain of f. Oh, that's just a line. I guess that's all real numbers. We'll look at the domain of G. That's just a line too. Well then, I guess we can say the domain of H is all reals. Just kidding, we can't. That's trash. Because it is possible for g of x to be 0. Where is g of x 0? Where is 2x plus 6 equal to 0? That happens when x is equal to negative 3. You can work that out somewhere if you want. The actual working it out would not be worth marks. So do it on scrap paper if you feel like it. So if x is negative 3, 2x plus 6 is equal to 0, which means that this is equal to 0. That means we're dividing by 0. That's a bad. So therefore, x cannot be negative 3. It can otherwise be any real number. Just not negative 3. It's like, I'll eat any vegetable, just not zucchini. You know? Just not that one. That's a lie. I don't like eggplant either. So we can still have any real number, just not negative 3. Oh, somebody forgot how to draw a curly bracket. Nope. Focus, determination. Try the other ones out. Of course, you can pause this video as per usual. And I'm just going to keep going. You control the pace here. Oops, 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 oops. There is the domains of the original functions. Y equals log x, well, you need x to be positive. Y equals x squared plus 1, that's quadratic. That has no restrictions, that can be any real number. Their overlap then is this business that x has to be positive. The other thing to consider, as usual, is where is g of x equal to 0? Well, x squared plus 1 is always positive, so we don't have any additional restrictions in this case. Phew, thank goodness. That saves us so much writing. So then the domain of h here is just that x has to be positive. And then the last one. F of x is on top. G of x is on Zabum bum. Oh, I forgot what subtraction looks like. Boom. I check out my domain of F. There we go. Except notation wise. Ooh. Nailed it. So we've got our radical function, we've got our quadratic function. Our denominator could be equal to 0. If we solve that, when is x squared minus 4 equal to 0? Happens a couple times. So when we look at the collective domain for our quotient function, youch! All the x values, but they have to meet multiple criteria here. They have to be greater than or equal to -5, and they cannot be any version of 2, and are otherwise real numbers. As long as it meets all this criteria, we good. If it meets this criteria, that means we're actually taking a value from f of x. If it meets this criteria, that means we're not dividing by 0. So all restrictions are met. There is some practice work. Do try these concept questions. They're pretty cool. Really try all of them. And as usual, please let me know if you have questions or comments or concerns. Miss you all so much. Pretend I gave you a handshake or a fist bump. Obviously, I still wouldn't do that if I saw you in person right now because, you know, who knows if I've coughed on these hands. Keep it real. Goodbye.